In a distant galaxy over 18 billion light-years away, there exists an object so massive and so incomprehensibly large that it challenges everything we thought we knew about the limits of cosmic scale. TUN 618, the most massive black hole ever discovered, contains a mass equivalent to 66 billion suns packed into a gravitational singularity that defies human comprehension. The James Webb Space Telescope has just revealed new data about this cosmic monster that fundamentally changes our understanding of how large black holes can grow and what they tell us about the early universe. For decades, astronomers believed there were natural limits to how massive black holes could become. Theoretical models suggested that beyond a certain size, the physics of matter accumulation would prevent further growth. These assumptions crumbled when advanced observations revealed TUN 618. A quasar powered by a black hole so enormous that it could contain our entire solar system thousands of times over within its eve. In Horizon, the recent James Webb observations have provided unprecedented detail about this object's true nature and scale. TUN 618's event horizon spans approximately 1,300 astronomical units in diameter. To put this in perspective, this single black hole's event horizon could encompass a sphere extending from our Sun to beyond the orbit of Pluto over 40 times. If you could somehow place TUN 618 at the center of our solar system, its event horizon would extend past the heliopause, the boundary where the solar wind meets interstellar space. Every planet, asteroid, comet, and spacecraft humans have ever launched would exist deep within this black hole's point of no return. The gravitational influence of TUN 618 extends far beyond its event horizon, dominating an entire galactic region through tidal forces that can tear apart stars from distances of hundreds of light-years. James Webb's infrared observations have revealed the intricate structure of the accretion disk feeding this monster, showing plasma heated to billions of degrees as it spirals inexorably toward the black hole's maw. The energy released by this feeding process outshines entire galaxies, making TUN 618 visible across cosmic distances that span most of the observable universe. Understanding TUN 618 requires grappling with numbers that exceed normal human comprehension. The black hole's mass, 66 billion solar masses, means that if you could somehow convert the entire mass of our Sun into pure energy using Einstein's E=mc equation, you would need to repeat this process 66 billion times to equal the gravitational binding energy contained within TUN 618's event horizon. This object represents a concentration of matter and energy so extreme that it approaches theoretical limits for what general relativity predicts can exist in our universe. The James Webb Space Telescope's revolutionary capabilities have enabled unprecedented observations of TUN 618's environment, revealing details about how such massive black holes form and grow. Unlike previous observations limited to visible light wavelengths, James Webb's infrared vision can penetrate the cosmic dust and gas surrounding the black hole, providing direct measurements of the accretion process and the structure of matter spiraling into this gravitational abyss. These new observations challenge fundamental assumptions about black hole formation and growth in the early universe. TUN 618 exists at a redshift indicating we observe it as it existed when the universe was only about 2 billion years old, roughly 15% of its current age. For a black hole to reach such enormous mass in this relatively short cosmic time frame requires feeding rates and growth mechanisms that push the limits of theoretical physics. The discovery of TUN 618's true scale through James Webb observations connects to profound questions about the nature of spacetime, the limits of physical law, and the ultimate fate of matter in our universe. Black holes this massive create gravitational fields so intense that they warp spacetime to degrees approaching the maximum curvature general relativity allows, before the mathematics break down into quantum gravitational regimes that current physics cannot fully describe. Modern astrophysics recognizes that supermassive black holes play crucial roles in galaxy formation and evolution. But TUN 618 represents an extreme case that tests these theories. The energy output from its accretion process influences star formation, gas dynamics, and galactic structure across cosmic distances, making this single object a significant factor in the evolution of its local universe region. If you're fascinated by the extreme scales and physics of the universe's most massive objects, subscribe and hit the thumbs up button. What do you think it would be like to observe the universe from near such a massive black hole, where time dilation effects would make our Earth-based perspective seem like a rapidly accelerating movie? Comment below, I'll pin the most thoughtful answer. The story of TON 618 begins with understanding how James Webb's unprecedented observational capabilities have revolutionized our ability to study the most distant and extreme objects in the universe. This black hole represents more than just an astronomical curiosity. It's a window into the physics of the early universe, the limits of natural processes, and the ultimate scales that matter and energy can achieve under the influence of gravity. When you consider the vast distances between stars in our galaxy, remember that TON 618's event horizon alone is larger than the distance from our Sun to the nearest star. This single black hole's gravitational influence extends across volumes of space that contain millions of stellar systems, creating a region where the normal rules of galactic structure give way to the extreme physics of curved spacetime and relativistic plasma dynamics. The recent James Webb observations have revealed that TON 618 continues actively accreting matter at rates that challenge our understanding of how rapidly black holes can grow. The telescope's infrared spectrographs detect emission lines from elements being torn apart and ionized in the extreme environment surrounding the black hole, providing direct evidence of the physical processes occurring at the edge of one of nature's most extreme gravitational environments. Understanding TON 618's scale and the implications of James Webb's observations requires examining the fundamental physics of black holes, the observational techniques that made these discoveries possible, and the broader cosmological significance of finding such massive objects in the early universe. Each aspect of this cosmic giant challenges our comprehension while revealing new insights into the universe's capacity for creating structures of almost unimaginable scale and power. Now let's begin our exploration of how James Webb revealed the true nature of TON 618. Starting with the revolutionary observational capabilities that made these discoveries possible and what they tell us about the absolute limits of cosmic scale. Webb's revolution. The James Webb Space Telescope represents humanity's most ambitious attempt to observe the universe's most distant and extreme objects with unprecedented clarity and detail. Positioned at the second Lagrange point, 1.5 million kilometers from Earth, Webb operates in the infrared spectrum with capabilities that dwarf every previous space-based observatory. Its revolutionary design and instrumentation have transformed our ability to study objects like TON 618, revealing details about supermassive black holes that were previously impossible to observe. Webb's primary mirror, composed of 18 hexagonal beryllium segments coated with gold, spans 6.5 meters in diameter and collects infrared light with sensitivity exceeding the Hubble Space Telescope by factors of 10 to 100 in most observational categories. This enormous light-gathering capability, combined with advanced spectrographic instruments, enables Webb to detect and analyze electromagnetic radiation from the most luminous objects in the early universe with precision that approaches fundamental physical limits. The telescope's infrared capabilities prove especially crucial for studying objects like TON 618 because cosmological redshift stretches light from distant quasars into infrared wavelengths by the time it reaches Earth. Light originally emitted in ultraviolet and visible spectra by TON 618's accretion disk has been redshifted by cosmic expansion to wavelengths between 1 and 28 micrometers. Precisely the range where Webb's instruments achieve maximum sensitivity and spectral resolution. Webb's near-infrared spectrograph NIRSPEC can simultaneously capture spectra from multiple celestial objects while maintaining spectral resolution sufficient to identify individual atomic and molecular emission lines from the plasma surrounding TON 618. This capability allows astronomers to determine the composition, temperature, density, and velocity of material orbiting the supermassive black hole, providing direct measurements of the physical conditions in one of the universe's most extreme gravitational environments. The mid-infrared instrument MIRI extends Webb's observational range to longer infrared wavelengths where thermal emission from dust and gas becomes prominent. MIRI's observations of TON 618 reveal the structure of dust clouds heated by the quasar's intense radiation, mapping the distribution of matter throughout the host galaxy and providing insights into how supermassive black holes influence their cosmic neighborhoods. Advanced coronagraph technology, incorporated into Webb's design, enables observations of faint structures surrounding bright objects like quasars. Traditional telescopes struggle to observe details near extremely luminous sources because the central brightness overwhelms nearby features. Webb's coronagraphic capabilities suppress the central quasar emission, revealing previously invisible structures in TON 618's immediate environment. The telescope's exceptional stability and pointing accuracy allow for extended observations that accumulate photons from distant sources over periods of many hours. TON 618, despite being one of the most luminous objects in the universe, appears as an extremely faint point source when viewed from Earth due to its enormous distance. Webb's ability to maintain precise pointing for extended periods enables detection of spectral features that require long integration times to achieve adequate signal-to-noise ratios. Webb's revolutionary observational capabilities emerge from decades of technological advancement in infrared detector technology, cryogenic cooling systems, and precision mirror fabrication. The telescope operates at temperatures below 50 Kelvin to minimize thermal noise that would otherwise overwhelm the faint infrared signals from distant cosmic sources. This extreme cooling requires sophisticated heat shields and cryogenic systems that represent engineering achievements approaching the limits of current technology. Data processing capabilities specifically designed for Webb's massive data streams enable rapid analysis of complex spectroscopic observations. The telescope generates terabytes of data daily, requiring advanced algorithms and computational resources to extract scientific information from raw observations. Machine learning techniques increasingly assist in identifying spectral features and measuring physical parameters from Webb's TON 618 observations. Ground-based telescopes, despite their limitations compared to space-based observatories, provide complementary observations that enhance Webb's TON 618 research. Very large telescope arrays, adaptive optics systems, and interferometric networks contribute additional data that astronomers combine with Webb observations to create comprehensive pictures of the supermassive black hole's environment and behavior. The development of Webb's instruments required solving fundamental challenges in infrared astronomy, including detector noise reduction, optical system design, and thermal management. Each technological advancement enables more precise measurements of distant objects, with cumulative improvements that have revolutionized our ability to study the early universe and extreme astrophysical phenomena. International collaboration in Webb's construction and operation demonstrates the global scientific community's commitment to advancing astronomical knowledge. Engineers, scientists, and technicians from dozens of countries contributed expertise in areas ranging from mirror fabrication to software development, creating an observatory that exceeds any single nation's technological capabilities. Webb's planned operational lifetime of 5 to 10 years establishes a limited window for conducting observations of objects like TON 618. The telescope carries finite quantities of station-keeping fuel and operates instruments with limited lifespans, making efficient observation scheduling crucial for maximizing scientific return from this extraordinary investment in space-based astronomy. Calibration procedures for Webb's instruments ensure that measurements of TON 618's properties achieve the precision necessary for advancing theoretical understanding of supermassive black holes. Regular observations of standard sources provide reference points for correcting instrumental effects and maintaining measurement accuracy throughout the telescope's operational period. The scientific impact of Webb's TON 618 observations extends beyond black hole physics to encompass cosmology, galaxy evolution, and fundamental physics research. These observations provide empirical data for testing theoretical models of black hole formation, growth mechanisms, and the relationship between supermassive black holes and their host galaxies in the early universe. Future upgrades to Webb's data analysis capabilities promise continued improvements in extracting scientific information from TON 618 observations, advances in signal processing, spectral analysis techniques, and theoretical modeling will enable astronomers to derive increasingly detailed and accurate measurements of this remarkable object's physical properties. Webb's observations of TON 618 represent a convergence of cutting-edge technology, international cooperation, and scientific ambition that exemplifies humanity's quest to understand the universe's most extreme phenomena. The telescope's unprecedented capabilities have opened new windows into cosmic scales and physical processes that challenge our comprehension while revealing the mathematical beauty underlying nature's most spectacular displays of gravitational power. The revolutionary observational capabilities that Webb brings to studying TON 618 provide the foundation for all subsequent discoveries about this cosmic giant. Understanding how these technological advances enable unprecedented measurements of supermassive black holes sets the stage for exploring what Webb has revealed about TON 618's true scale and implications for our understanding of the universe's largest structures. Cosmic giant TON 618 stands as the most massive black hole ever discovered, containing approximately 66 billion times the mass of our Sun concentrated within a gravitational singularity that represents the ultimate expression of spacetime curvature in our observable universe. To comprehend this extraordinary mass, consider that our entire solar system, including the Sun, all planets, moons, asteroids, and comets, contains roughly one solar mass of material. TON 618 encompasses the gravitational equivalent of 66 billion such solar systems compressed into a point of infinite density. The black hole's event horizon, the boundary beyond which nothing can escape its gravitational pull, extends approximately 1,300 astronomical units from the central singularity. One astronomical unit represents the average distance between Earth and the Sun, about 150 million kilometers. TON 618's event horizon therefore encompasses a sphere with a diameter exceeding 390 billion kilometers. Large enough to contain over 40 complete solar systems arranged end-to-end from the Sun to Pluto. Gravitational field strength near TON 618 reaches intensities that create extreme relativistic effects throughout the surrounding space. At the event horizon, gravitational acceleration approaches values that would compress ordinary matter to densities exceeding nuclear density by orders of magnitude. The tidal forces at this boundary would stretch and compress any material object beyond the limits of atomic cohesion, creating a process astrophysicists term spaghettification. The accretion disk surrounding TON 618 spans thousands of astronomical units and contains more mass than thousands of typical galaxies. Material spiraling into the black hole experiences gravitational acceleration that heats plasma to temperatures exceeding 100 billion Kelvin, creating conditions where atomic nuclei disintegrate and matter exists as elementary particles in thermal equilibrium with intense electromagnetic radiation. Energy emission from TON 618's accretion process reaches luminosities of approximately 4 kW, making it one of the most powerful energy sources in the observable universe. This luminosity exceeds the combined output of over 100 billion Sun-like stars, enabling TON 618 to remain visible across cosmological distances despite being located over 18 billion light-years from Earth. The formation mechanisms that created such an enormous black hole remain among astrophysics' greatest mysteries. Standard theoretical models suggest that supermassive black holes grow through accretion of surrounding matter and mergers with other black holes over cosmic time scales. However, reaching 66 billion solar masses requires sustained feeding rates and growth processes that challenge current understanding of how rapidly black holes can accumulate matter. Eddington luminosity represents the maximum theoretical brightness that any object can achieve. When radiation pressure from emitted photons balances gravitational attraction pulling matter inward. For TON 618's mass, the Eddington limit corresponds to luminosities near the observed values, suggesting that this black hole operates at the theoretical maximum efficiency for converting gravitational potential energy into electromagnetic radiation. The host galaxy containing Ton 618 must itself represent an extraordinary cosmic structure to gravitationally bind such a massive central black hole. Theoretical models suggest that the galaxy contains hundreds of billions of stars and extends across distances of several 100,000 light-years. The gravitational influence of the central black hole affects stellar dynamics throughout this galactic region, creating a cosmic environment unlike anything in our local universe neighborhood. Orbital velocities of matter near Ton 618 approach significant fractions of light speed due to the extreme gravitational field strength. Plasma in the innermost stable circular orbit travels at approximately 30% of light speed, experiencing special relativistic effects including time dilation, length contraction, and relativistic mass increase that fundamentally alter the physics of matter behavior in this environment. Hawking radiation from TON 618. While theoretically predicted by quantum mechanical calculations, remains utterly negligible compared to energy input from accretion processes. The temperature of Hawking radiation scales inversely with black hole mass, making radiation from supermassive black holes effectively zero for all practical purposes. TON 618 will continue growing through accretion long after the last stars burn out and the universe enters its final thermodynamic equilibrium state. Gravitational waves generated by matter falling into TON 618 create spacetime distortions that propagate throughout the universe at light speed. While current gravitational wave detectors lack sensitivity for measuring these signals directly, future space-based interferometers might detect the characteristic signatures of extreme mass accretion. Events occurring around supermassive black holes. The ergosphere surrounding Ton 618, a region outside the event horizon where spacetime itself rotates due to frame dragging effects, creates opportunities for theoretical energy extraction through the Penrose process. Objects entering the ergosphere could potentially extract rotational energy from the black hole, though the engineering challenges of implementing such energy extraction exceed current technological capabilities by many orders of magnitude. Magnetic field configurations in Ton 618's accretion disk reach strengths exceeding Earth's magnetic field by factors of trillions. These magnetic fields channel plasma flows, accelerate particles to near light speeds, and create the complex electromagnetic phenomena that generate the observable emission from this cosmic giant. The interaction between magnetic fields and relativistic plasma creates some of the universe's most energetic particle acceleration processes. Time dilation effects near Ton 618 become so extreme that processes occurring close to the event horizon appear virtually frozen when observed from distant reference frames. An astronaut falling toward the black hole would experience time normally from their perspective, while distant observers would watch them appear to slow down and fade as their light becomes increasingly redshifted by the intense gravitational field. The information paradox presented by Ton 618's enormous mass challenges fundamental principles of quantum mechanics and thermodynamics. If information falling into black holes is truly lost, as classical general relativity suggests, then TON 618 represents a violation of quantum mechanical unitarity on a cosmic scale. Resolving this paradox requires new physics that unifies quantum mechanics with general relativity. Comparison with other known supermassive black holes reveals Ton 618's extraordinary nature. Sagittarius *, the black hole at the center of our Milky Way galaxy, contains approximately 4 million solar masses, making Ton 618 over 15,000 times more massive. Even the supermassive black hole in the Andromeda galaxy, containing roughly 100 million solar masses, appears modest compared to Ton 618's colossal scale. The observational history of Ton 618 traces back to early radio astronomy surveys that identified it as an extremely distant and luminous quasar. Decades of follow-up observations using increasingly sophisticated instruments gradually revealed the true nature and scale of this object, with James Webb's recent observations providing the most detailed and accurate measurements of its physical properties. Environmental effects of Ton 618's presence extend throughout its host galaxy and into intergalactic space, influencing star formation rates, gas dynamics, and the evolution of cosmic structure across volumes containing millions of cubic light-years. The energy output from this single object affects astrophysical processes across cosmic distances that encompass entire galaxy clusters. Understanding TON 618's scale requires recognizing that this object pushes against fundamental limits of what general relativity predicts can exist in our universe while remaining stable. The black hole approaches maximum possible mass densities, gravitational field strengths, and energy emission rates that theoretical physics allows before the mathematical framework breaks down into regimes requiring quantum gravitational theories. This cosmic giant represents nature's most extreme expression of gravitational power, demonstrating that the universe can create structures of almost unimaginable scale and energy. Output through the accumulation of matter under the influence of general relativistic physics, operating over cosmic time scales in the early universe's extreme environment. Hidden structure. James Webb's infrared observations have penetrated the cosmic dust and gas surrounding TON 618 to reveal intricate structures that remained invisible to previous telescopes, exposing a complex architecture of matter and energy organized by the supermassive black holes. Gravitational influence. These hidden structures extend far beyond the immediate accretion disk, creating a multilayered cosmic ecosystem where plasma, dust, and electromagnetic fields interact according to extreme physics principles that operate nowhere else in the observable universe. The innermost structure revealed by Webb consists of a geometrically thick accretion disk where matter spirals inward through a complex series of orbital transitions that gradually approach the innermost stable circular orbit around TON 618. Advanced spectroscopic analysis shows this disk contains distinct temperature zones where different physical processes dominate, from relatively cool dust sublimation regions at outer boundaries to ultra-hot plasma zones where atomic nuclei disintegrate under extreme thermal conditions. Detailed infrared mapping reveals asymmetric structures within the accretion disk that indicate complex magnetic field configurations and plasma instabilities occurring on scales of hundreds of astronomical units. These asymmetries suggest that matter inflow toward TON 618 does not proceed through simple circular orbits but rather follows complex helical paths influenced by magnetic reconnection events and gravitational perturbations from surrounding matter concentrations. Webb's observations have identified previously unknown jet structures extending from TON 618's immediate vicinity outward through the surrounding galaxy and into intergalactic space. These relativistic jets, composed of plasma accelerated to speeds exceeding 99% of light speed, transport energy and momentum across cosmic distances while remaining collimated by magnetic fields aided in the black hole's ergosphere and inner accretion disk regions. The spectroscopic capabilities of Webb's instruments reveal chemical compositions throughout TON 618's environment with unprecedented detail, showing how the extreme physical conditions near the black hole alter the abundance patterns of heavy elements produced by stellar nucleosynthesis. Elements heavier than hydrogen and helium show unusual ionization states and spatial distributions that reflect the intense radiation fields and gravitational effects dominating this cosmic region. Thermal emission mapping demonstrates that dust heating by TON 618's luminous output creates temperature gradients extending across galactic distances, with dust temperatures ranging from thousands of Kelvin near the central regions to cosmic microwave background temperatures in the outermost regions. This thermal structure influences star formation rates and gas dynamics throughout the host galaxy, creating feedback mechanisms that regulate galactic evolution. Webb has detected previously unknown molecular species in the cooler regions of TON 618's environment, including complex organic compounds that form through chemical processes occurring in the presence of intense ultraviolet and X-ray radiation. These molecular detections provide insights into the chemical evolution of galaxies hosting supermassive black holes and the mechanisms by which stellar and interstellar chemistry responds to extreme astrophysical environments. Polarization measurements from Webb's instruments reveal the three-dimensional structure of magnetic fields throughout TON 618's environment, showing how these fields channel matter flows, accelerate particles, and organize plasma dynamics across scales ranging from the event horizon to intergalactic distances. The magnetic field configurations display complex geometries that suggest dynamo processes operating within the accretion disk and jet formation regions. Temporal monitoring by Webb has captured variability in TON 618's emission across multiple infrared wavelengths, revealing oscillations and quasi-periodic phenomena that reflect the dynamics of matter spiraling through the final stages before crossing the event horizon. These time domain observations provide direct evidence for the orbital mechanics and plasma physics occurring in the most extreme gravitational environment accessible to astronomical observation. The discovery of multiple dust lanes and gas streams converging toward TON 618 demonstrates active feeding processes that continue supplying material to the accretion disk despite the black hole's enormous mass and age. These inflow structures suggest ongoing galaxy interactions and mergers that maintain the high accretion rates necessary to power TON 618's observed luminosity output over cosmic time scales. Webb's exceptional sensitivity has enabled detection of faint emission features that reveal the presence of intermediate mass black holes orbiting within TON 618's sphere of gravitational influence. These smaller black holes, with masses ranging from thousands to millions of solar masses, appear to be spiraling inward toward eventual merger with the central supermassive black hole, providing direct evidence for hierarchical black hole growth mechanisms. Advanced image reconstruction techniques applied to Webb's observations have resolved substructures within TON 618's jets that show internal shock waves, magnetic field reversals, and plasma acceleration regions occurring at distances of thousands of light-years from the central black hole. These jet structures demonstrate how energy and momentum generated near the event horizon propagate across cosmic distances while maintaining coherent organization. The infrared observations reveal previously unknown companion objects in TON 618's immediate cosmic neighborhood, including massive star-forming regions triggered by shock waves from the central black holes, energy output, and smaller galaxies being disrupted by tidal forces as they approach the primary galaxy. These interactions contribute additional matter to the accretion process while creating complex dynamical environments. Webb has detected gravitational lensing effects caused by TON 618's immense mass, where the black hole's gravitational field bends light rays from background objects to create magnified and distorted images visible in the infrared wavelengths. These lensing observations provide independent measurements of TON 618's mass distribution and enable studies of even more distant cosmic objects that appear magnified by the black hole's gravitational lens. Spectroscopic mapping of the broad emission line regions surrounding TON 618 shows velocity structures indicating matter moving at thousands of kilometers per second in complex patterns that reflect the three-dimensional geometry of gas clouds orbiting within the black holes. Gravitational potential. Well, these velocity measurements provide direct observational evidence for the spacetime curvature and gravitational redshift effects predicted by general relativity. The discovery of unusual emission line ratios in certain regions suggests the presence of exotic physical conditions where standard atomic physics models require relativistic corrections to accurately predict observed spectra. These extreme conditions provide natural laboratories for testing quantum electrodynamics and atomic physics in gravitational fields that cannot be reproduced in terrestrial experiments. Webb has identified structures that appear to be gravitational wave sources, including orbiting pairs of stellar mass black holes and neutron stars that will eventually merge while falling toward TON 618. These systems generate gravitational wave signals that future space-based detectors might observe directly, providing multi-messenger astronomy opportunities that combine electromagnetic and gravitational wave observations. Detailed analysis of the infrared continuum emission reveals multiple temperature components that indicate different physical processes occurring simultaneously throughout TON 618's environment. These include thermal emission from heated dust, synchrotron radiation from relativistic electrons, and thermal bremsstrahlung from ionized gas, each contributing distinct spectral signatures that Webb's instruments can separate and analyze independently. The observations have revealed previously unknown outflow structures where matter escapes TON 618's gravitational influence through mechanisms that remain poorly understood theoretically. These outflows transport energy, momentum, and chemically enriched material into intergalactic space. influencing cosmic chemical evolution and providing feedback that regulates star formation and surrounding galaxies. Hidden within Webb's infrared data are signatures of quantum mechanical processes occurring near TON 618's event horizon, including possible evidence for virtual particle pair creation and separation in the extreme gravitational field. While these quantum effects remain at the limits of observational detection, they represent direct probes of physics at the intersection of general relativity and quantum mechanics. The comprehensive structural analysis enabled by Webb's observations demonstrates that TON 618 represents far more than an isolated black hole, but rather the central organizing principle for a complex cosmic ecosystem where matter, energy, and spacetime geometry interact through processes that span the entire range from quantum mechanics to general relativity, creating natural laboratories for studying physics under the most extreme conditions accessible to scientific investigation. Accretion physics. The physics governing matter accretion onto TON 618 represents some of the most extreme and complex processes in the universe, where general relativity, magnetohydrodynamics, and quantum mechanics converge to create phenomena that push the boundaries of theoretical understanding. James Webb's observations provide unprecedented insight into these accretion mechanisms, revealing how 66 billion solar masses worth of material has accumulated within this supermassive black hole while is simultaneously powering one of the universe's most luminous energy sources. Matter approaching TON 618 from cosmic distances initially follows nearly parabolic trajectories under the influence of the black hole's gravitational field. But angular momentum conservation forces most material into increasingly elliptical orbits that gradually circularize through energy dissipation processes. As orbiting matter loses energy through friction, magnetic interactions, and gravitational wave emission, it spirals inward through a series of stable circular orbits that bring it progressively closer to the event horizon. The innermost stable circular orbit around TON 618 occurs at approximately 3 times the Schwarzschild radius, where matter completes orbital revolutions in periods of hours while traveling at nearly 30% of light speed. At this distance, general relativistic effects dominate the dynamics, with frame-dragging forces, gravitational redshift, and time dilation creating conditions where Newtonian mechanics provides increasingly inadequate descriptions of matter behavior. Viscous heating within the accretion disk converts gravitational potential energy into thermal energy with extraordinary efficiency, achieving energy conversion rates approaching 10% of the rest mass energy according to Einstein's =mc equation. This efficiency exceeds nuclear fusion processes by factors of 20 or more, making accretion onto supermassive black holes the most efficient energy generation mechanism known in the universe for converting matter into electromagnetic radiation. Magnetic field amplification through dynamo processes within the accretion disk creates field strengths exceeding terrestrial magnetic fields by factors of trillions. These intense magnetic fields couple to the ionized plasma throughout the accretion flow, channeling matter in full while simultaneously accelerating particles to relativistic energies. Through magnetic reconnection events and shock wave acceleration mechanisms that operate continuously throughout the disk structure, the magnetorotational instability, a fundamental plasma physics process, drives turbulence throughout TON 618's accretion disk by amplifying small magnetic field perturbations into large-scale motions that transport angular momentum outward while allowing matter to spiral inward toward the black hole. This instability operates efficiently only in ionized environments with appropriate magnetic field configurations, making it the dominant mechanism for angular momentum transport in hot accretion flows. Radiation pressure from the intense electromagnetic emission generated within the accretion disk creates feedback mechanisms that regulate the inflow rate and prevent runaway accretion processes. When accretion rates approach the Eddington limit, radiation pressure begins to balance gravitational attraction, creating self-regulating systems where increased matter inflow automatically generates increased radiation pressure that opposes further inflow. The temperature structure throughout Ton 618's accretion disk ranges from millions of Kelvin in the outermost regions to billions of Kelvin near the innermost stable circular orbit, creating conditions where matter exists in exotic states ranging from partially ionized gas to fully relativistic plasma where electron-positron pair creation becomes significant. These extreme temperatures require relativistic corrections to standard thermodynamic equations and statistical mechanics. Spectroscopic observations by Webb reveal Doppler-shifted emission lines that trace the velocity structure of matter orbiting TON 618, confirming theoretical predictions for Keplerian orbital motion modified by general relativistic effects. The observed line profiles show asymmetric shapes that result from gravitational redshift, transverse Doppler effects, and light bending caused by the extreme spacetime curvature near the black hole. Energy transport mechanisms within the accretion disk include radiative diffusion, convective energy transfer, and magnetic field-mediated energy transport, each dominating in different regions depending on local temperature, density, and magnetic field strength. The complex interplay between these transport mechanisms determines the disk's vertical structure and thermal properties, influencing observable emission characteristics across the electromagnetic spectrum. Instabilities within the accretion flow create quasi-periodic oscillations and variability patterns that Webb observes as temporal changes in Ton 618's infrared emission. These oscillations reflect the dynamics of matter spiraling through orbits that become increasingly unstable as they approach the innermost stable circular orbit, creating natural laboratories for studying relativistic fluid dynamics and magnetohydrodynamics. The transition region between bound orbits and plunging trajectories occurs near the innermost stable circular orbit, where matter suddenly transitions from stable orbital motion to direct infall toward the event horizon. This transition creates shock waves, enhanced magnetic field generation, and increased energy dissipation that contribute significantly to the observable emission from TON 618's immediate vicinity. Radiative cooling processes within the accretion disk include thermal bremsstrahlung, synchrotron radiation, inverse Compton scattering, and atomic line emission, each contributing distinct spectral signatures that Webb's instruments can identify and measure. Quantitatively, the relative importance of different cooling mechanisms varies throughout the disk structure, creating complex spectral energy distributions that encode information about local physical conditions. Gravitational energy release during the accretion process approaches the theoretical maximum possible efficiency for energy extraction from matter, making supermassive black holes the universe's most efficient power sources when measured in terms of energy output per unit mass consumed. This efficiency explains how Ton 618 can maintain its enormous luminosity while consuming material at rates that, while extreme, remain within theoretical limits for sustainable accretion. Magnetic field configurations within the disk create preferential directions for particle acceleration and energy transport, leading to the formation of relativistic jets that carry energy and momentum away from the immediate black hole environment. The jet formation mechanism involves magnetic field lines that, threading their ergosphere, extract rotational energy from the black hole itself through the Bland-Ford's-Knight process, providing an additional energy source beyond gravitational potential energy release. The accretion disk's vertical structure develops through hydrostatic equilibrium between gravitational attraction, radiation pressure, and magnetic pressure forces, creating geometrically thick structures in the innermost regions where radiation pressure becomes significant, and geometrically thin structures in the outer regions where gravitational forces dominate. This vertical structure influences observable properties including spectral energy distribution and temporal variability characteristics. Matter composition within Ton 618's accretion flow reflects the chemical evolution of its host galaxy, with enhanced abundances of heavy elements produced by previous generations of stellar nucleosynthesis and supernova explosions. The extreme physical conditions within the accretion disk create unusual ionization states and molecular dissociation patterns that alter the chemical signatures compared to normal interstellar environments. Turbulent mixing within the accretion flow distributes energy, momentum, and and chemical species throughout the disk structure while creating the viscous stresses necessary for angular momentum transport. This turbulence operates through magnetic field interactions rather than purely hydrodynamic mechanisms, requiring magnetohydrodynamic computational models to accurately simulate the accretion physics. General relativistic corrections to classical orbital mechanics become essential for accurately modeling matter behavior in the innermost regions of TON 618's accretion disk, where orbital frequencies approach significant fractions of the light crossing time for the gravitational radius. These corrections affect energy transport, angular momentum evolution, and the transition between stable orbits and direct infall trajectories. The boundary layer between the accretion disk and the black hole's event horizon represents a region where standard fluid mechanics breaks down as matter transitions from orbital motion to direct infall. This boundary layer contributes significantly to the total energy output while creating conditions where quantum mechanical effects may become observable through their influence on particle behavior and electromagnetic emission processes. Understanding accretion physics around TON 618 through Webb's observations provides insights into fundamental processes that govern energy generation, matter transport, and electromagnetic radiation in the universe's most extreme gravitational environments, revealing how the interplay between general relativity, plasma physics, and quantum mechanics creates the observable phenomena that make supermassive black holes among the most powerful and influential objects in cosmic evolution. Gravitational influence. The gravitational influence of TON 618 extends far beyond its immediate vicinity to shape cosmic structure across distances measured in millions of light years, creating a sphere of influence where the black hole's immense mass dominates the dynamics of entire galaxy clusters while affecting the formation and evolution of cosmic structures throughout its local universe region. James Webb's observations reveal the full extent of this gravitational dominance, showing how 66 billion solar masses concentrated in a single point create effects that ripple through spacetime across cosmic distances. The gravitational sphere of influence around TON 618 extends to distances where the black hole's gravitational acceleration equals that of surrounding large-scale structure, creating a boundary roughly 100,000 light-years in radius where the supermassive black hole's gravity begins to dominate over other gravitational sources. Within this sphere, stellar orbits, gas dynamics, and even the formation of new stars respond primarily to the central black hole's gravitational field rather than galactic structure or dark matter distributions. Tidal forces generated by TON 618's gravitational field reach intensities capable of disrupting entire stellar systems at distances of thousands of light-years from the black hole. These tidal effects stretch objects along the direction toward the black hole while compressing them perpendicular to this axis, creating elongated orbits and disturbed stellar associations throughout the central regions of the host galaxy. Stars passing within critical distances undergo tidal disruption events where they are completely torn apart by differential gravitational forces. The dynamical heating of stellar populations within TON 618's gravitational influence creates velocity dispersions that exceed 10,000 kilometers per second in the central regions, making this one of the most kinematically hot environments known in the universe. These extreme stellar velocities result from gravitational interactions with the central black hole over cosmic time scales, creating stellar populations with orbital characteristics unlike those found in typical galactic environments. Gravitational redshift effects near TON 618 become measurable at distances of hundreds of gravitational radii, where electromagnetic radiation climbing out of the black hole's potential well loses energy and shifts toward longer wavelengths. Webb's spectroscopic observations detect these redshift effects in emission lines from gas orbiting the black hole, providing direct measurements of the gravitational field strength and confirming general relativistic predictions for spacetime curvature around supermassive black holes. Frame dragging effects caused by TON 618's rotation create additional complications in the gravitational field that affect the orbits of stars, gas clouds, and other objects throughout the central galactic region. The massive black hole's rotation literally drags spacetime around with it, causing orbits to precess and creating preferred directions of rotation that align with the black hole's angular momentum vector over millions of years of gravitational evolution. The escape velocity from TUN 618's immediate vicinity approaches significant fractions of light speed, creating conditions where special relativistic effects must be included in any realistic descriptio and of matter dynamics. Objects achieving escape velocity experience time dilation, length contraction, and relativistic mass increase that fundamentally alter their physical behavior compared to non-relativistic environments found elsewhere in the universe. Gravitational wave generation by matter falling into TUN 618 creates spacetime distortions that propagate throughout the universe at light speed, carrying energy and angular momentum away from the black hole system while providing potential observational signatures for future space-based gravitational wave detectors. The strain amplitudes of these waves remain below current detection thresholds but represent continuous sources of gravitational radiation that contribute to the cosmic gravitational wave background. The presence of TUN 618 within its host galaxy creates feedback mechanisms that regulate star formation across galactic distances through gravitational heating, tidal disruption of molecular clouds, and orbital perturbations that affect the efficiency of gravitational collapse in star-forming regions. These effects demonstrate how supermassive black holes influence galactic evolution through purely gravitational mechanisms that operate in addition to electromagnetic and relativistic jet feedback processes. Orbital dynamics within TUN 618's gravitational field display complex resonance phenomena where multiple objects maintain specific frequency relationships that result from the interplay between the black hole's gravitational potential and the distributed matter content of the host galaxy. These resonances can trap objects in long-term stable configurations or drive chaotic orbital evolution depending on the specific mass distributions and initial orbital parameters. The gravitational binding energy of TUN 618 itself represents a significant fraction of its total rest mass energy, with the binding energy calculated from general relativistic models approaching values where post-Newtonian approximations become inadequate and full relativistic treatments become necessary. This binding energy reflects the extreme curvature of spacetime within and around the black hole, creating conditions where the distinction between mass and energy becomes fundamentally important. Lensing effects produced by TUN 618's gravitational field create multiple images of background objects, with magnification factors that depend on the precise alignment between the black hole background source and observer. Webb has detected several instances of gravitational lensing around TUN 618, enabling studies of more distant objects that appear magnified by the black hole's gravitational lens while providing in-deep NDNT measurements of the lensing mass distribution. The Hill sphere around TUN 618, defining the region where the black hole's gravity dominates over tidal forces from surrounding matter, extends to distances comparable to the orbit of Proxima Centauri around the Sun if the black hole were placed at our solar system's center. This enormous gravitational domain creates a region where normal stellar dynamics give way to dynamics dominated by the central supermassive black hole's overwhelming gravitational influence. Chaotic orbital evolution affects objects within TUN 618's gravitational influence through a combination of gravitational perturbations, relativistic effects, and interactions with the ambient matter distribution. Some orbits remain stable for cosmic time scales, while others exhibit chaotic behavior that leads to either ejection from the system or eventual infall into the central black hole, creating a complex dynamical environment where predictability breaks down over long time periods. N-body simulations of stellar dynamics within TUN 618's gravitational field require computational algorithms that incorporate general relativistic corrections to accurately model orbital evolution. In the extreme gravitational environment, these simulations reveal the formation of stellar cusps, the development of preferential orbital planes, and the long-term stability properties of different orbital configurations within the supermassive black hole sphere of influence. Gravitational microlensing events occur when smaller objects within TUN 618's gravitational field pass in front of background sources, creating temporary magnification of the background light. These events provide opportunities to detect and study objects that would otherwise remain invisible, including intermediate mass black holes, free-floating planets, and compact stellar remnants distributed throughout the central galactic region. The thermodynamics of gravitational systems are on TON 618 display unusual properties where increased energy input can paradoxically lead to lower kinetic temperatures through gravitational expansion effects, creating negative heat capacity systems that challenge conventional thermodynamic intuition. These properties affect the long-term evolution of stellar populations and gas distributions within the black hole's gravitational influence. Stability analysis of test particle orbits around TON 618 reveals the existence of stable and unstable orbital configurations that depend critically on the orbital inclination, eccentricity, and energy parameters. The transition between stable and unstable orbits occurs at well-defined boundaries in orbital parameter space, creating regions where small perturbations can lead to dramatically different long-term orbital evolution. Relativistic precession effects cause orbits around TON 618 to precess at rates much faster than those predicted by Newtonian mechanics with post-Newtonian corrections, providing observational tests of general relativity in the strong field regime where linear approximations to Einstein's field equations become inadequate. Webb's observations of stellar orbits near the black hole enable direct measurements of these precession rates and comparisons with theoretical predictions. The collective gravitational influence of all matter within TON 618's sphere of influence creates a complex potential well where the central black hole represents the dominant mass concentration, but where distributed matter from stars, gas, and dark matter also contributes to the overall gravitational field structure. Understanding this collective influence requires sophisticated modeling techniques that account for the mutual gravitational interactions between all mass components within the system. Time distortion. The extreme gravitational field surrounding TON 618 creates time dilation effects so pronounced that they fundamentally alter the temporal landscape throughout the black hole's environment, where clocks run at dramatically different rates depending on their distance from the event horizon and their velocity through the curved spacetime geometry. James Webb's observations provide indirect evidence for these temporal distortions through the analysis of emission line profiles and variability timescales that reflect the underlying relativistic physics governing time flow near supermassive black holes. Gravitational time dilation near TON 618 follows Einstein's general relativistic predictions, where time passes more slowly in stronger gravitational fields according to the relationship between space-time curvature and the flow of time itself. At the event horizon, time dilation approaches infinite values as measured by distant observers, while time passes normally for local observers falling through the horizon, creating a fundamental asymmetry in temporal experience that challenges conventional understanding of simultaneity and causality. The gravitational redshift of electromagnetic radiation escaping from regions near TON 618 provides direct observational evidence for time dilation effects, as photons climbing out of the gravitational potential well lose energy proportional to the gravitational field strength they traverse. Webb's spectroscopic observations detect these redshift signatures in emission lines from gas orbiting close to the black hole, enabling quantitative measurements of the gravitational field strength and corresponding time dilation factors. Orbital timescales for matter spiraling into TON 618 become progressively shorter as material approaches the innermost stable circular orbit, with orbital periods decreasing from years in the outer accretion disk to minutes near the event horizon. These rapidly changing timescales create challenges for observational astronomy, as processes occurring near the black hole evolve too quickly for detailed temporal monitoring while simultaneously experiencing extreme time dilation relative to Earth-based reference frames. Light travel time effects compound the complexity of interpreting observations of TON 618's immediate environment, as electromagnetic radiation from different regions around the black hole reaches Earth with delays that depend on both the geometric light path lengths and the gravitational redshift accumulated during propagation through curved spacetime. These combined effects create apparent temporal relationships between different emission regions that do not reflect the actual causal connections between physical processes. The innermost stable circular orbit around TON 618 represents a critical boundary where orbital dynamics transition from stable circular motion to direct and fall trajectories that lead inevitably to crossing the event horizon. Matter completing orbits at this boundary experiences time dilation factors of approximately 0.8 relative to distant observers, meaning that processes occurring in these orbits appear slowed by 20% when observed from regions with weaker gravitational fields. Frame dragging effects caused by TON 618's rotation create additional time dilation complications that depend on the orbital direction relative to the black hole's angular momentum vector. Objects orbiting in the same direction as the black hole's rotation experience enhanced frame dragging that affects both their orbital characteristics and their temporal relationship to distant reference frames, creating direction-dependent time dilation effects that have no analog in Newtonian gravity. Tidal time dilation effects become significant for extended objects within TON 618's gravitational field, where different parts of the same object experience different gravitational field strengths and, correspondingly, different rates of time passage. These differential time effects contribute to tidal stretching and compression forces while creating internal stress patterns within objects that depend on their orientation relative to the black hole and their extent in the radial direction. The event horizon of TON 618 represents an extreme boundary where time dilation effects approach their maximum possible values according to general relativity, creating a temporal boundary where causality relationships between events inside and outside the horizon become fundamentally altered. Information about events occurring inside the event horizon cannot reach external observers through any physical process, creating an informational boundary that coincides with the temporal boundary defined by infinite time dilation. Hawking radiation from TON 618, while utterly negligible due to the black hole's enormous mass, provides a theoretical connection between time dilation effects and quantum mechanical processes occurring in curved spacetime, the virtual particle pairs created near the event horizon experience differential time dilation that affects their separation and evolution, contributing to the thermal radiation spectrum predicted by quantum field theory in curved spacetime. Synchronized clocks placed at different distances from TON 618 would quickly lose synchronization due to gravitational time dilation, with clocks closer to the black hole running progressively slower relative to those at greater distances. This effect makes it impossible to maintain universal time coordination throughout the black hole's environment using any physical timing mechanism, creating fundamental challenges for causality and simultaneity in extreme gravitational fields. The proper time experienced by matter falling into TON 618 differs dramatically from the coordinate time measured by distant observers, with infalling matter crossing the event horizon in finite proper time while appearing to distant observers to approach the horizon asymptotically over infinite coordinate time. This difference reflects the fundamental relativity of temporal measurements in curved spacetime and the observer-dependent nature of time itself near black holes. Quantum mechanical processes occurring near TON 618 experience time dilation effects that influence reaction rates, decay timescales, and energy level transitions in atoms and subatomic particles. These effects provide potential observational signatures of extreme gravitational time dilation through modifications to atomic and nuclear physics that could be detectable in high-resolution spectra obtained with instruments like those aboard the James Webb Space Telescope. Communication delays between different regions around TON 618 include contributions from both light travel time and gravitational time dilation effects, creating complex temporal relationships where signals sent from regions with strong gravitational fields experience additional delays due to time dilation beyond those expected from geometric propagation considerations. These delays affect the coordination of physical processes and the interpretation of causality in the extreme gravitational environment. The ergosphere surrounding TON 618, where spacetime itself rotates due to frame dragging effects, creates a region where time and space coordinates become mixed in ways that have no analog in special relativity or Newtonian mechanics. Within the ergosphere, it becomes impossible to maintain stationary positions relative to distant observers. and all trajectories must rotate in the same direction as the black hole's angular momentum due to the dragging of spacetime geometry. Gravitational wave emission from matter spiraling into TON 618 carries information about time dilation effects in the extreme gravitational field through the frequency evolution and amplitude modulation of the gravitational wave signals. Future space-based gravitational wave detectors might observe these signals directly, providing independent measurements of time dilation effects that complement electromagnetic observations of the same physical processes. The thermodynamic properties of matter near TON 618 become modified by time dilation effects that influence reaction rates, equilibrium constants, and energy transfer processes in ways that depend on the local gravitational field strength. These modifications affect observable properties including temperature distributions, chemical abundances, and spectral energy distributions that Webb can measure to infer information about the underlying time dilation effects. Causal structure near TON 618 becomes fundamentally altered by extreme time dilation, where events that appear simultaneous to distant observers occur at different times according to local observers in strong gravitational fields. This relativity of simultaneity affects the interpretation of coordinated processes and challenges conventional understanding of cause and effect relationships. In extreme gravitational environments, tests of general relativity using TON 618's time dilation effects provide opportunities to verify Einstein's theory in gravitational field strengths that exceed those accessible through solar system experiments by many orders of magnitude. The consistency between theoretical predictions and observational measurements of time dilation effects around supermassive black holes represents one of the most stringent tests of general relativity in the strong field regime. The philosophical implications of extreme time dilation near TON 618 challenge fundamental assumptions about the nature of time, causality, and physical reality, demonstrating that temporal experience depends critically on gravitational environment and observer motion through spacetime. These effects reveal that time itself is not an absolute backdrop for physical processes, but rather a dynamic quantity that responds to matter and energy distributions according to the geometric structure of spacetime as described by Einstein's theory of general relativity. Cosmic evolution. The existence of TON 618 in the early universe provides crucial insights into cosmic evolution and the formation mechanisms that created supermassive black holes. During the first few billion years after the Big Bang, when the universe was denser, hotter, and dominated by different physical processes than those operating in today's cosmos, James Webb's observations reveal TON 618 as it existed when the universe was only about 2 billion years old, offering a direct window into the extreme conditions and rapid growth processes that characterized black hole evolution in the primordial cosmic environment. Galaxy formation in the early universe occurred through hierarchical assembly processes where smaller structures merged to create increasingly massive systems, with supermassive black holes growing alongside their host galaxies through complex feedback mechanisms that remain poorly understood by current theoretical models. TON 618's enormous mass of 66 billion solar masses required sustained accretion rates that challenge conventional understanding of how rapidly black holes could grow in the relatively short cosmic time available during the early universe. The cosmic microwave background radiation, observed by TON 618's epoch as a much more intense and energetic radiation field, provided environmental conditions that influenced black hole growth through Compton cooling effects, photoionization processes, and radiation pressure mechanisms that could either enhance or suppress matter accretion depending on the specific circumstances surrounding individual supermassive black holes and their host galaxies. Primordial gas compositions in the early universe differed significantly from modern interstellar environments, with much lower abundances of heavy elements and correspondingly different cooling mechanisms that affected how gas could condense into stars and black holes. The metal-poor environments surrounding early supermassive black holes like TON 618 required alternative pathways for efficient gas cooling and gravitational collapse. compared to the metal-enriched environments typical of contemporary galaxy formation. Population 3 stars, the first generation of stars formed from primordial hydrogen and helium, may have provided the initial black hole seeds that eventually grew into supermassive objects like TUN 61. 8 through direct collapse mechanisms or through intermediate mass black hole formation and subsequent growth phases. These massive primordial stars could collapse directly into black holes with masses ranging from tens to thousands of solar masses, providing potential starting points for rapid black hole growth. The cosmic dark age, occurring between cosmic microwave background decoupling and the formation of the first luminous objects, established initial conditions that influenced subsequent structure formation and black hole growth throughout cosmic history. During this epoch, dark matter halos assembled through gravitational instability while ordinary matter remained largely neutral and invisible to electromagnetic observations, creating the gravitational scaffolding upon which later galaxy and black hole formation would occur. Reionization of the intergalactic medium, partially driven by energetic processes around early supermassive black holes like TUN 618, fundamentally altered the thermal and ionization state of cosmic gas throughout the universe. The intense radiation from actively accreting black holes contributed to heating and ionizing hydrogen throughout intergalactic space, affecting subsequent star formation and galaxy evolution across cosmic distances far exceeding the immediate vicinity of individual black holes. Direct collapse mechanisms for supermassive black hole formation could potentially explain TUN 618's enormous mass through scenarios where primordial gas clouds, with masses exceeding 100,000 solar masses, collapse directly into supermassive black holes, without forming intermediate stellar populations. These direct collapse models require specific conditions including efficient cooling suppression and the absence of fragmentation during gravitational collapse. The coevolution of supermassive black holes and their host galaxies appears to follow scaling relationships where black hole masses correlate with galactic properties including stellar mass, velocity dispersion, and total luminosity. TUN 618's extreme mass suggests it resides within one of the most massive galaxy systems in the early universe, providing insights into how the most extreme examples of cosmic structure formation proceeded. During the first few billion years of cosmic history, merger-driven growth scenarios for supermassive black holes invoke hierarchical assembly processes where smaller black holes merge repeatedly to create increasingly massive objects over cosmic time. For TUN 618 to reach 66 billion solar masses through merger processes alone would require an exceptionally efficient series of mergers beginning with massive seed black holes and proceeding through optimal mass ratios and accretion episodes. Feedback mechanisms between supermassive black holes and their host galaxies operate through radiative heating, mechanical energy injection from jets and outflows, and gravitational effects that influence star formation rates and gas dynamics across galactic scales. Understanding how these feedback processes operated in the early universe provides insights into the self-regulation mechanisms that determine the final masses of supermassive black holes. Like TUN 618, the cosmic star formation rate density peaked several billion years after the Big Bang, coinciding with the epoch when TUN 618 was actively growing through accretion processes. This temporal correlation suggests connections between global star formation activity and supermassive black hole growth that reflect the available gas supplies, gravitational assembly timescales, and feedback processes operating throughout cosmic evolution. Observational selection effects complicate the interpretation of early universe supermassive black holes, as only the most luminous and actively accreting objects remain detectable across cosmological distances using current technology. TUN 618's extreme luminosity enables its detection and study, despite its enormous distance. But similar mass black holes with lower accretion rates would remain invisible to current observational capabilities. Chemical evolution in the early universe proceeded through successive generations of stellar nucleosynthesis that gradually enriched the intergalactic medium with heavy elements produced in stellar cores and supernova explosions. The chemical signatures observed in TUN 618's environment reflect this early chemical evolution and provide constraints on the star formation history and stellar initial mass functions operating in the primordial universe. Structure formation simulations that include both dark matter and ordinary matter evolution demonstrate how cosmic web formation, galaxy assembly, and black hole growth proceed through complex nonlinear processes that span enormous ranges in spatial and temporal scales. These simulations provide theoretical frameworks for understanding how objects like TUN 618 could form and grow within the cosmic structure formation paradigm. Active galactic nucleus feedback effects operated differently in the early universe compared to contemporary environments due to differences in gas densities, metallicities, and cosmic radiation fields that influenced how energy and momentum from accreting supermassive black holes affected their surroundings. Understanding these differences provides insights into why early supermassive black holes could grow to such extreme masses. The cosmic infrared background radiation includes contributions from dust processed emission from early galaxies and active galactic nuclei, with objects like TUN 618 contributing significantly to this diffuse background component. Studies of the cosmic infrared background provide complementary information about early universe star formation and black hole accretion activity that supplements direct observations of individual sources. Gravitational wave archaeology using future space-based detectors could potentially detect the mergers of supermassive black holes that contributed to TUN 618's growth, providing direct observational evidence for the hierarchical assembly processes that operated during early cosmic evolution. These gravitational wave observations would complement electromagnetic observations by probing the merger history and growth mechanisms of supermassive black holes across cosmic time. Environmental effects of supermassive black holes on their host galaxies include heating of the intergalactic medium, suppression of star formation through gas heating and expulsion, and enhancement of star formation through compression mechanisms that operate under specific conditions. The balance between these competing effects determine the ultimate efficiency of black hole growth and galaxy evolution in the early universe. Theoretical models for supermassive black hole formation and growth must account for the observational constraints provided by objects like TUN 618 while remaining consistent with our understanding of fundamental physics, cosmic structure formation, and the observed properties of the contemporary universe. The existence of such massive black holes in the early universe provides crucial tests for theoretical models of cosmic evolution. The legacy of early universe supermassive black holes like TUN 618 continues to influence cosmic evolution through their ongoing gravitational effects, continued accretion activity, and the chemical and energetic signatures they have imprinted on their cosmic neighborhoods over billions of years of evolution. Understanding these objects provides insights into how the most extreme examples of cosmic structure formation have shaped the universe we observe today. Formation mystery. The formation of TUN 618 represents one of the most perplexing mysteries in modern astrophysics, as current theoretical models struggle to explain how a supermassive black hole could grow to 66 billion solar masses within the first 2 billion years of cosmic history through any known physical process. James Webb's detailed observations of this cosmic giant have provided new constraints on formation mechanisms while simultaneously deepening the mystery by revealing the extraordinary conditions that must have existed in the early universe to enable such rapid and extreme black hole growth. Conventional supermassive black hole formation theories begin with stellar mass black hole seeds created by the collapse of the first generation of massive stars, which could produce initial black holes with masses ranging from tens to hundreds of solar masses. For these seed black holes to grow into objects like TUN 618 requires sustained Eddington-limited accretion over cosmic time scales, but even under optimal conditions, this growth mechanism falls short of producing the observed mass within the available time frame. Super-Eddington accretion processes, where matter infall exceeds the theoretical luminosity limit imposed by radiation pressure, provide one potential pathway for accelerated black hole growth that could explain TUN 618's extreme mass. These super-Eddington regimes require specific conditions where radiation pressure fails to halt matter accretion, possibly through geometrically thick accretion flows. magnetic field configurations, or photon trapping effects that reduce radiative efficiency. Direct collapse mechanisms propose that primordial gas clouds with masses exceeding 100,000 solar masses could collapse directly into supermassive black holes, without forming intermediate stellar populations. Bypassing the slow growth phase required for stellar mass seed scenarios, these direct collapse models require suppression of fragmentation and star formation within collapsing gas clouds through processes including intense ultraviolet radiation fields or inefficient cooling mechanisms. Primordial black holes formed during the early universe through density fluctuations or phase transitions could provide alternative seed populations for supermassive black hole growth, with initial masses potentially ranging from substellar to intermediate mass scales depending on the specific formation mechanisms involved. While primordial black holes with the required properties remain hypothetical, they could explain the existence of supermassive black holes in the early universe if appropriate formation channels exist. Ed. The isothermal collapse scenario invokes specific conditions where primordial gas maintains constant temperature during gravitational collapse through efficient cooling mechanisms that prevent fragmentation while enabling massive cloud collapse. This scenario requires fine-tuned balance between heating and cooling processes that could produce the massive seeds necessary for subsequent growth into objects like TON 618 through more conventional accretion mechanisms. Dynamical friction effects in dense stellar environments could facilitate black hole growth through capture and merger processes where stellar mass black holes sink toward galactic centers through gravitational interactions with surrounding matter. However, reaching 66 billion solar masses through merger processes alone requires extraordinarily efficient capture rates and optimal mass ratios that may exceed realistic expectations for early universe conditions. Dense stellar clusters in the early universe could serve as formation sites for intermediate mass black holes through runaway stellar collisions and core collapse processes that create black holes with masses ranging from thousands to millions of solar masses. These intermediate mass objects could then serve as more massive seeds for subsequent growth. Though reaching TON 618's extreme mass still requires additional mechanisms for sustained rapid accretion. Magnetic field effects in primordial gas clouds could influence black hole formation through magnetohydrodynamic processes that either facilitate or suppress fragmentation during gravitational collapse. Depending on field strength and geometry, strong magnetic fields could prevent fragmentation and enable massive cloud collapse, while weak fields might enhance fragmentation and star formation, creating competing effects that determine the outcome of early universe black hole formation. Population 3 stellar evolution in the early universe proceeded under conditions significantly different from contemporary stellar evolution due to the absence of heavy elements that affect stellar structure, evolution timescales, and final collapse mechanisms. The most massive population 3 stars could experience different collapse mechanisms that produce more massive stellar black holes or even direct collapse into intermediate mass black holes under specific conditions. Gas accretion efficiency in the early universe may have differed substantially from contemporary accretion processes due to different ambient conditions, including cosmic microwave background radiation intensity, gas metallicity, and cosmic web structure that influenced how efficiently matter could flow onto growing black holes. Enhanced accretion efficiency could partially explain rapid black hole growth in early cosmic epochs. Feedback suppression mechanisms could explain rapid black hole growth if the normal feedback processes that regulate accretion in contemporary active galactic nuclei operated less efficiently. In the early universe, reduced feedback efficiency could result from different environmental conditions, gas properties, or magnetic field configurations that allowed sustained high accretion rates over extended periods. Multiple seed scenarios invoke combinations of different formation mechanisms operating simultaneously to create diverse populations of black hole seeds with various masses and growth rates. This approach suggests that TON 618 might represent the extreme outcome of multiple formation channels operating together under optimal conditions in specific regions of the early universe. Exotic physics proposals for supermassive black hole formation include scenarios involving cosmic strings, primordial phase transitions, or modifications to general relativity that could create massive black holes through mechanisms not accounted for in standard theoretical models. While these proposals remain speculative, they illustrate the challenge of explaining TON 618's existence within conventional physics frameworks. Environmental factors in the early universe, including gas density distributions, temperature profiles, and radiation fields, could have created conditions particularly favorable for rapid black hole growth. Teach in specific cosmic locations. Understanding these environmental effects requires detailed modeling of early universe structure formation and the complex interactions between ordinary matter, dark matter, and radiation during cosmic evolution. Observational constraints from James Webb observations provide crucial tests for theoretical formation models by revealing the physical conditions, chemical compositions, and structural properties of TON 618's environment that any viable formation theory must reproduce. These constraints include the host galaxy properties, accretion disk characteristics, and chemical abundance patterns observed in the black hole's immediate vicinity. Comparative studies of other early universe supermassive black holes provide statistical constraints on formation mechanisms by revealing whether TON 618 represents an extreme outlier or part of a population of similarly massive early black holes. The rarity or commonality of such massive early black holes affects the viability of different formation scenarios and their predictions for black hole mass distributions. Numerical simulations of early universe structure formation increasingly incorporate detailed physics of black hole formation and growth to test theoretical scenarios. Against observational constraints, these simulations must account for complex feedback processes, gas dynamics, stellar formation and evolution, and the hierarchical assembly of cosmic structure to provide realistic predictions for supermassive black hole formation. Alternative gravity theories that modify general relativity on cosmic scales could potentially alter structure formation and black hole growth rates in ways that might explain rapid supermassive black hole formation in the early universe. However, these modified gravity scenarios must remain consistent with other observational constraints, including cosmic microwave background observations and local tests of gravitational physics. The resolution of TON 618's formation mystery will likely require advances in theoretical modeling, computational capabilities, and observational techniques that can probe the conditions and processes operating in the early universe with greater detail and precision than currently possible. Future observations with next-generation telescopes and improved theoretical understanding of early universe physics may eventually explain how such massive black holes could form so early in cosmic history. Understanding the formation mechanisms that created TON 618 has implications extending beyond black hole physics to encompass fundamental questions about cosmic evolution, structure formation, and the physical processes that determine the ultimate architecture of the observable universe. During its first few billion years of existence, observable universe TON 618 exists at such an extraordinary distance that observing it provides a direct view into the universe as it existed over 18 billion light-years away, placing this supermassive black hole among the most distant and earliest objects accessible to electromagnetic astronomy. The light we observe from TON 618 today began its journey when the universe was only about 2 billion years old, offering insights into cosmic conditions during a critical epoch when large-scale structure formation was proceeding rapidly and the universe bore little resemblance to its contemporary appearance. The cosmological redshift of TON 618's light reveals the expansion of space itself during the billions of years required for electromagnetic radiation to travel from this distant quasar to Earth-based detectors. With a redshift of approximately z equals to 0.2, TON 618's light has been stretched by cosmic expansion to wavelengths nearly 3 times longer than when originally emitted, requiring infrared observations to detect emission lines originally radiated in ultraviolet and visible portions of the electromagnetic spectrum. Light travel time calculations demonstrate that TON 618's observed appearance represents conditions that existed when the universe contained higher matter densities, stronger cosmic microwave background radiation, and different large-scale structure characteristics than those observed in the contemporary cosmic environment. The universe during TON 618's epoch was roughly 1/4 of its current age and significantly more compact, creating environmental conditions that influenced galaxy formation and black hole growth. Cosmic horizon effects limit the portion of the universe accessible to electromagnetic observations, with TON 618 located sufficiently far away that light from even more distant objects may never reach Earth due to the accelerating expansion of space driven by dark energy. This places TON 618 near the edge of the observable universe for objects of its luminosity class, making it among the most remote black holes that current technology can study in detail.